are going to start this discussion with the topic of principal component analysis. If you recall MANOVA was all about partitioning the total variability in the data into components which were due to the different sources of variation. Now, principal component analysis, it also tries to explain the total data variability present with the help of a fewer number of linear combinations of the original data, meaning if I have a p-dimensional random data vector, say, which means that I have p random vectors x1, x2 to xp, say. Now, I am going to explain the total variability present in the data with the help of k new variables, say y1, y2 to yk, where k is a number which is much less than p, and these yi's are actually linear combinations of the original variables x1, x2 to xp. So basically you can see the broad objective of principal component analysis is reduction in the data dimension. Now, once the reduction in data dimension is achieved, we achieve many more things, and one of the most important of which is interpretation, data projection, etc. Okay. Now, strictly speaking, all the p variables are required if I want to explain the variability, the total variability present in the data. But in most situations, we will see that a fewer number of the linear combinations of these variables will be good enough to explain the total variability. Now, in common parlance, this is said that the information content of the variables x, that is x1, x2, xp, is as much as the information content of the, or conversely we should say that the information content of the new variables y's are as much as the information content of the original variables. But we should take this with a bit of caution, and we must remember that this is with respect to the total variation in the data. Okay. So, let us say first just very briefly write what is principal component analysis. Our new topic, this what it is doing in this analysis, what we are basically doing is a PCA is concerned with explaining the variance covariance structure. When we say the variability, the total variability in the data, this is through the variance covariance matrix of the random vector. How exactly that we will see once we define total variability in the data. So, variance covariance structure of a set of variables through a few this few can be really very few, like even k equal to 2 or 1 may be also good enough to explain the total variability through a few linear combinations of these variables. Why do we do a principal component analysis? So, broad objectives of PCA are, the first one is data reduction, rather we should say data dimension reduction. And the second one being data interpretation. Now, in between there are many things before we can correctly interpret the data. So, we will look into all these aspects. So, these are the two broad objectives, but in between there are many more other analysis that will help us. So, and besides an analysis of the PCA, it also in time it reveals some interesting relationships among the variables, among the p variables, which were not apparent otherwise. So, with the the crux of the matter always remains the dimensionality reduction. So once we do this, we can see that I can project the new variables, the two-dimensional variables, say y1 and y2, and I can have a clear idea about the data cluster, or if there is an outlier in the data. And of course, while we calculate the principal components, we get interesting relationships among the variables. So how is this done? So first we have, the whole thing is based on the variance covariance matrix. So what we have is the random vector x, which is a p-dimensional data vector, x1 to xp, and that's a p-dimensional random vector with variance covariance matrix sigma. A very general sigma, elements are sigma ij, and we prefer to write it in this way, sigma 1 1 sigma 1 2 to sigma 1 p, and this is a symmetric matrix, so you can write 1 p or p1, which means basically sigma ij is equal to sigma ji. So that's a p by p dimensional square matrix, and we assume positive definiteness of this matrix. Now we have been saying that total variability in the data, total variability in x is going to be explained through the total variability of y, the new variables. So what we exactly mean by total variability or total variation in data, and how is the variance covariance matrix coming into the picture with this concept. So total variation or total variability also we may say in x, this is nothing but trace of the variance covariance matrix. It's as simple as that. So this is by definition. So total variation in x is nothing but the trace of sigma, which means that I consider sum of the diagonal elements, sum of the variances, that is summation sigma I from 1 to p. And then what does PCA attempt to do? PCA aims to replace the x, this x, the whole data vector, with some y, okay, and initially we will look into p linear combinations of the variables. So that's y also p dimensional, y1 to yp, but firstly where these yi's, these are not just any variables, these are linear combinations of the original variables xi's, linear combinations of xi's, but not just any linear combinations. We must satisfy certain conditions such that the first thing is I have to remember the yi's are uncorrelated. Note that we have not taken xi's to be uncorrelated, because I have never said that sigma is a diagonal matrix, just a general variance covariance matrix, which means xi's can be correlated also. But the linear combinations through which now we are going to explain the total variability, these new variables yi's, they have to be uncorrelated, that is covariance between yi and yj, this is equal to 0 for every I not equal to j. This is the first point. The second one is the very thing that we have started with, that total variation in x. We say that the information content of y is as good as the information content of x with respect to the total variability present in the data. So which means the total variation in x is equal to the total variation of y. But then why do we choose to work with the y if this is the situation? Because here comes the most important point, that the total variation of total variation of y, which is of y1 to yp, this is actually almost equal, approximately equal to the total variation of y1 to yk. So, this is approximately equal to total variation of y. When I say total variation of y, I mean that all p members of y are present, but the crux of the matter is this total variation can be explained with a much less number of variables y1 to yk. So, when I say much less number of variables, I mean that k is where k is really less than p, much less than the total dimension p. Okay. So, these are the three basic features of the new variables, the principal components, which are basically the linear combinations of the original variables that we have listed here. They form the crux of the whole exercise, and we have to be careful in constructing our principal components in a manner so that all these three properties are satisfied. Now, before we formally define principal component, let us talk about some of the other uses of principal components. We have said the broad objectives are data dimension reduction and data interpretation. In between, there are some other tasks that we can accomplish through the construction of principal components, and these are, write down the major uses of principal components or principal component analysis. What all can be achieved through a PCA is, of course, the first thing is the data dimension reduction, and everything else that follows is basically is essentially following from this fact. So, data dimension reduction. The second one of importance is, once there is dimension reduction, we can project the data in a two-dimensional plane, or at the most a three-dimensional plane, to properly visualize the whole thing. So, data projection and visualization. This is possible if we can achieve a value of k equal to 2 or at the most 3, so that all the properties that we have listed are satisfied. If that can be done, then projection and visualization can be done in a really nice manner. The third one is, once we project the data, then there are certain features of the data that become apparent to us. That is, we can see formation of data clusters. So, idea about data clusters, the various groupings of the data, and of course, if we can project the data in a two-dimensional plane, we can also see if there is any outlier present in the data. So, that is multidimensional outlier handling. So, multidimensional outlier detection, that also can be done. And fifth, there can be some ranking of the multidimensional data also, ranking of multidimensional data. And projection of the data can also tell us whether the population, whether the data comes from a multivariate normal population or not. So, that is checking for multivariate normality. So, we can handle as many things with a PCA, and all of these are very important practical application, practical uses for the multidimensional data. Checking for, last one is checking for multivariate normality. Next, we are going to define formally what is a principal component, and we say that, well, we have already talked about it. They are basically linear combinations of the original variables such that certain properties are satisfied. So, definition of principal components. The principal components are the uncorrelated linear combinations y1, y2 to yp. Note that initially we talk about as many number of linear combinations of y's of x's as there are number of x variables. So, we talk about y1, y2 to yp when we have x1, x2 to xp, but ultimately we will work with a much fewer number of y's, so y1, y2 to yk. So, initially we say that there are p such linear combinations. P is equal to the number of data variables that we have originally. So, linear combinations y1, y2 to yp whose variances are in decreasing order. So, now this is something which you are saying for the first time. Uncorrelatedness, of course, we have said before. Now, something more we are saying that we have y1, y2 to yp, the variances of these y1, y2 to yp, they are in decreasing order. So, what we have is variance of y1, that is maximum. So, these are in decreasing order. So, y1 explaining the maximum variability, y2 explaining the second highest variability, and so on. Now, it's very logical that we have this criterion on the principal components, because our ultimate aim is to restrict the number of principal components to as few as possible. So, if this can be possible, if only the first one, it can explain the maximum of the variability. So, it can be so high that sometimes we may be satisfied with the first principal component only, and then in that case we will say that the whole data dimensionality has been reduced to 1. We are happy with a value of k equal to 1, as low as that. Okay. So, we must have the principal components designed in this fashion, y2 explaining the second highest variability, and so on. Okay. So, what are the things that we are talking about? That is, let us now try to sum up the situation. The first principal component, the first PC, is the linear combination. Well, we are using the notations y's for the principal components. So, the first principal component is the linear combination y1, the first one. This is L1 dash L1 prime x. So, this is essentially a p-dimensional vector, known vector it should be, so that y1 is known, what is the linear combination of x that I am using for y1, that I am getting for y1. So, that is y1 is L1 transpose x such that maximizes variance of L1 x subject to L1 transpose L1 is equal to 1. Now, why is this required? Now, I say that this y1 formed as L1 transpose x, it should be such that variance of L1 transpose x is maximum. Now, that can be if I consider any other scalar multiplication of the linear of this vector L1, and I consider say some L1 star, which is C times L1. C is a very high constant. So, then I can always have variance of C L1 transpose x greater than variance of L1 transpose x. So, to put a check on that and to achieve some uniqueness, I require this factor. I put this criterion that it is subject to L1 transpose L1 is equal to 1. Then the second, the principal component is the linear combination y2. This is some other linear combination of the x's x1, x2 to xp such that the variance is maximizes variance of y2, that is L2 prime x, subject to L2 transpose L2 is 1, and we must have something else here, and covariance between y2 and y1 is 0, that is L1 prime x and L2 prime x. This is equal to 0. And in this way I go to the ith principal component. The ith principal component is the linear combination yi is Li transpose x, that maximizes the variance of Li transpose x, subject to, as before, Li transpose Li, this is equal to 1, and covariance between Li x with say some Lkx, this is equal to 0, and now this has to be true for all k which is less than I. Right. So, if I go to the third principal component, I must check the covariance between the third and the second and the third and the first as well, and both of these have to be equal to 0. Now, what I am saying here, will this guarantee me the things that I have said before? That is, the first thing was that the principal components have to be uncorrelated, they should maximize or the first one should have the maximum variance, the second principal component should have the second highest variance, and so on. The total variability of these y's should be equal to the total variability of x, and last but not the least, the total variability of y can be explained through the variability of a very few number of y's. Okay. So, all these things, whether those can be satisfied with this type of a construction that I am saying. Okay. So, for this we go on to the next thing. Let us see that the way that we are saying the principal components we are describing, they can in fact satisfy all the properties. So, the first result is, let sigma be the covariance matrix, the variance covariance or the dispersion matrix associated with the random vector x. The whole exercise will be done through the eigenvalue eigenvectors of this sigma matrix. Okay, so, with the random vector x, the eigenvalue and eigenvector, orthonormal eigenvector. So, corresponding orthonormal eigenvector pairs of this sigma matrix are L1, E1, P of them, so up to LP, EP. Okay. Let us say where I have lambda 1 greater than equal to lambda 2 and greater than equal to lambda p. So, this is how I have arranged the eigenvalues and the corresponding orthonormal eigenvectors, and I have this lambda 1 greater than equal to lambda 2 up to lambda p. So, these are in decreasing order, and each of them of course are greater than equal to 0, means for positive semi-definiteness also we can have, strictly speaking, but most of the situations we will have this as positive definite matrix. Okay. So, leave it like this, and then the ith PC is given by, we say that the ith PC is given by yi. This simply turns out to be EI transpose x for every I from 1 to p. So, after having said all these things, what we do is simply consider the sigma matrix, calculate the eigenvalue and the corresponding orthonormal eigenvector, and we will see that the ith principal component is nothing but a linear combination of this type, where we are taking help of the orthonormal eigenvector. So, the linear combination that I have is yi is nothing but ei transpose x. Now, if yi's are this other properties satisfied, they will be satisfied, because simultaneously we have something for these yi's. These are for every I from 1 to p with variance of yi. We will see that this is nothing but lambda I for every I from 1 to p. So, that another property, if you recall, of the principal component is satisfied, that is, the first principal component will satisfy the maximum variability, its variance will be higher than the variances of all other principal components. So, this is true if I have the variance of yi equal to lambda I. The first principal component will have variance lambda 1, which is greater than lambda 2 to lambda p, and so on. And another thing was, whether these are uncorrelated, we will see that covariance between yi and yj will be 0 for all I not equal to j. Okay. So, let us prove this result. We have made a strong statement that the linear combinations or the principal components are nothing but the linear combinations of x's along with the orthonormal eigenvectors simply of the dispersion matrix. So, for the proof of the result, we start with, let us consider variance of L prime x. Okay, I consider one linear combination of x and I check its variance, which is nothing but L transpose variance of x starting from the scratch, and this is nothing but L prime sigma L, and this I prefer to write by after using the spectral decomposition of the sigma matrix. So, I have P d lambda P transpose L. Now, I have already said that, so this sigma is given in terms of its spectral decomposition P d lambda P prime. I have already said that eigenvalues of sigma are lambda 1 to lambda p and E1 to EP are the corresponding orthonormal eigenvectors. So, I know the structure of d lambda, this is nothing but diagonal lambda 1 to lambda p, and the P matrix has E1 to EP as its columns. Okay. So, P is an orthogonal matrix. Now, this is something like I can write for this L prime P d lambda P prime L, I can write it something as beta transpose d lambda beta, where beta is nothing but P prime L, right. And that is, well, that is nothing but I have a beta vector, I have a diagonal matrix whose diagonal elements are lambda i's and then beta vector again. So, that is nothing but a summation of the type beta I square lambda I from 1 to p. Now, what I am required to do is to get, so I have beta is P prime L. So, this also implies that L is nothing but, if you consider L, what you have to do is simply pre-multiply this with P transpose inverse. That is possible because P is an orthogonal matrix, and since P is orthogonal, this is nothing but L is nothing but P beta. Okay. And P beta, this relationship gives me a very important thing, that L transpose L equal to 1 implies that you have beta transpose P transpose P and then again beta is equal to 1, and that implies beta transpose beta is also equal to 1. So, L transpose 1 equal to 1 is equivalent to saying beta transpose beta is also equal to 1. So, that now that I have to maximize variance of L transpose x over L such that L transpose L is equal to 1. So, this can be said that equivalently I can maximize this expression, which I have shown to be equal to the variance. I have to maximize summation beta I square lambda I over beta such that, well, such that beta transpose beta is equal to 1, and in terms of summation I can write this as such that beta I square is equal to 1. Now, I have summation beta I square, that's the variance of L prime x. So, I can, if I can obtain an upper bound of this expression subject to the condition that summation beta I square equal to 1, then I am through. So, I am trying to look into it. So, I have summation beta I square lambda I sum from I from 1 to p. This has to be less than or equal to if I replace all the eigenvalues with the maximum eigenvalue. So, I am writing lambda 1 for all lambda i's, and hence I get this less than equal to sign, and then this summation beta I square remains there, right. So, I have, and then when I have this is equal to lambda under the condition since summation beta I square is equal to 1. So, I have achieved that maximum of variance L prime x maximum over L such that L prime L is equal to 1 is nothing but lambda 1, because I have shown that this variance of L prime x is nothing but this summation beta I square lambda I, and the condition is nothing but summation beta I square equal to 1. And then I have seen, I have shown that I can obtain an upper bound of this term, and it is nothing but the maximum eigenvalue lambda 1. So, this has been shown that variance of L1 prime x under the condition L prime L equal to 1, maximum of that is equal to lambda 1. Now, I consider variance of y1 and y1, the one that is given to me, that is variance of E1 prime x. Y1 is said to be equal to this linear combination, and this is equal to E1 prime sigma E1, and this is again by using the spectral decomposition of sigma. This is P d lambda P prime E1, right. Again I can handle this. I have write this E1 prime. For the P matrix I am writing E1, E2 to EP, and then I have the diagonal matrix D lambda. I am writing P transpose matrix E1 transpose to EP transpose, and then E1 again. If this is so, by the fact that these EIs are orthonormal, I will have this operation here combining this vector and this matrix is going to give me the vector 1 and then followed by 0, and here I have the diagonal matrix, and similarly I have the vector this one here. So, this is nothing but lambda 1, because the first diagonal element of d lambda is lambda 1, and only this is coming into the picture with 1 as the members here. So, that is essentially 1 times d lambda, and that is lambda 1, which is equal to maximum of variance lambda L prime x maximum over L such that L prime L is equal to 1. This is actually equal to this maximum variance which we have seen just now. So, I have y1 equal to E1 prime x is the first PC, because as far as the first PC is concerned, I will have to check only one thing, that its variance is having the maximum variance, and if its variance is lambda 1 and it is greater than all other lambda eigenvalues, and it is actually equal to maximum of variance L prime x, the maximum over this choice of L with only this condition in place, L prime L equal to 1. Well, I have achieved the whatever criterion, the single criterion that was required for my first principal component, and I have y1 is E1 prime x is the first principal component. Then I go to the next one, that is construction of the second principal component, and next we consider the second principal component. So, next we consider y2, linear combination, another linear combination of the original variables x1 to xp such that y2, now here we have to remember two things. Firstly, that y2 is uncorrelated with y1, this factor did not come when we were considering the first principal component, and secondly, the variance of y2 has to be less than variance of y1. So, these two properties have to be satisfied in the construction such that y2 is uncorrelated with y1, this is number 1, and so that is what we are getting is that implies that covariance of y1 and y2, this has to be equal to 0. So, we are considering covariance between L prime x, and now we know what is y1. So, I take that form of y1 E1 prime x, and if you see that this is nothing but it's nothing but you have L prime x minus its expectations. So, this is something we are introducing here. We are assuming that the main vector is of x is mu. So, that is there, and then I have E1 prime x minus E1 prime mu. This expectation is nothing but L prime sigma E1, this is equal to 0. So, this is giving me L prime sigma E1, this is nothing but L prime, and I consider another alternative form of the spectral decomposition of sigma. We know that this sigma, which is p d lambda p prime, can also be written in the summation form, that with lambda I, the scalars, and then the vectors coming into the picture. It is not pi's but ei's, we are denoting them by ei's. So, this is lambda I ei prime, sum from 1 to p. So, we use this form here for sigma, this form of the spectral decomposition. This is a summation lambda I ei prime, I from 1 to p, and then you have E1. So, this fact is leading me to this covariance being equal to 0, because this is nothing but you have lambda 1 only coming out and L prime is combining with E1, and this is equal to 0 implies that L is orthogonal to E1. Okay. So, covariance of this equal to 0 is leading me to the fact that this L has to be constructed in such a way such that this is orthogonal to the vector which is coming in the first principal component, that is E1. Okay. And then we have to consider the maximum of variance L prime x maximum over L, such that now we have, as we have two properties of y2 to satisfy. So, similarly we have two conditions, two types of conditions on L. One is there already, which we know that L transpose L has to be equal to 1, and the other one is something which we have seen just now, that L has to be orthogonal to E1. So, these two conditions have to be simultaneously satisfied, and then we have to get the maximum variance of L prime x. So, how is this done? We have variance of L prime x, this is nothing but L prime sigma L, and let us use the usual form of spectral decomposition. We have E1 to EP, this is how I am writing the matrix P, then I have d lambda, and then P transpose E1 transpose to EP transpose with L in the end. This is L transpose. So, this is giving me L transpose. We have earlier seen that L transpose P d lambda P prime L is something like B transpose d lambda B, which is some 0 to B2 to BP we have in place, because all I have the condition that I have is L prime is orthogonal to E1 and not so with the other E vectors. So, I have 0 to B2 to BP and then d lambda, and then I have the null the vector this B2 transpose to BP transpose, right. So, this is these are essentially scalars. So, we are talking about the elements of the B vector. So, these what we have here, this is fine, and this is the elements of the B matrix. So, I have 0 to B2 from B2 to BP, right. So, this is like a summation Bi square with lambda I from 2 to P, right. So, for all so this is obviously for all L which is orthogonal to E1, we have used this factor. And how is this coming? Moreover, we have certain other things to be followed. We have B is nothing but, if you see that B has been replaced for P prime L, so that L is nothing but P B, and L prime L equals 1 implies that you have B transpose P transpose P B, which is equal to B transpose B, this is equal to 1. So, the whole condition structure can be reduced to this fact that I have to maximize variance of L prime x subject to that L is orthogonal to E1 and L transpose L is equal to 1. Okay. Now, with L orthogonal to E1, I have seen I just saw that this variance L prime x is nothing but equal to summation Bi square lambda I. Now, again I have to consider its maximum with the fact that beta prime B prime B is equal to 1, because one condition I have already incorporated while I got the form, this summation Bi square is lambda I. I have already incorporated the condition that L is orthogonal to E1. I have got yet one more condition to be satisfied, that is B transpose B is equal to 1. So, I have to consider the maximum of this expression summation Bi square lambda I such that summation Bi square is equal to 1. Okay. So, this implies that I have maximum of variance L prime x maximum over L such that L is orthogonal to E1. Let us write this first, because this condition has been taken care of in the first place, and then I have L prime L is equal to 1 is nothing but maximum of summation Bi square lambda I from 2 to P summation over maximum over B such that sum of Bi square I from 2 to P is equal to 1, right. So, this can be achieved if again I replace the lambda i's by their maximum value. Now, here the lambda i's are from 2 to P. So, the maximum value of this lambda 2 to lambda P is nothing but lambda 2, and then I have this as, so this here I can replace this by equality by less than or equal to, and this by summation Bi square 2 to P and this is equal to lambda 2. So, I have seen that if I consider this second principal component, its variance is lambda 2, which is less than lambda 1. So, its variance is actually less than variance of y 1. Not only that, this covariance of y 1 and y 2 considered in this way is also equal to 0. So, I have successfully constructed the second principal component. Therefore, I can write it here just one line. This implies that y 2 equals to E2 x is the second. Before that, let us just check the variance of E2 x, and just the way we have done in the case of the first principal component, and then only we can comment on that. Now, next, variance of y2, which is variance of E2 x, right. This is nothing but E2 transpose sigma E2, and this is E2 transpose. You have the P matrix, we are using the same form P d lambda P prime, the spectral decomposition. So, we have E1 to EP, then d lambda, then we have E1 transpose to EP transpose L2, sorry, it is not L but E2, right, and this is nothing but, because E2 is orthonormal to all these, in fact E1 to EP are all orthonormal eigenvectors, you will have E2 combining with E2 only, and since these are orthonormal, you get 1 here. So, this is basically 0, 1, 0, 0, then you have d lambda, and then again 0, 1, 0 to 0, which gives you lambda 2. So, all these things sum up to the conclusion that this implies y2 is E2 prime x is the second principal component. So, in this way we can go up to the k plus 1th one, say likewise after the kth principal component, the k plus 1th principal component. So, after going to the first, the second, and then we go to the third principal component is for the k plus 1th principal component, we must have maximum of variance of L prime x. L is now orthogonal to E1 to E2 to all these EKs, right. K plus 1 is less than all 1, 2 to K plus 1 being less than 1, 2 to K. So, L has to be orthogonal to each of these, and of course, the original condition that L transpose L is equal to 1, and this will be nothing but maximum of L with E1 to Ek, and then you have Ek plus 1 to EP, then d lambda transpose of these E1 to Ek, Ek plus 1 to EP, and then you have L, right. So, this is going to give you, so you have variance of L prime x is now going to be 0 for k times, and then you have L prime Ek plus 1, and then up to L prime EP. L is not orthogonal with this, then you have d lambda, and similarly you have this 0, and then again you have L prime Ek plus 1 up to L prime EP, right. So, this variance is nothing but, this implies that you have a situation where this you can define some vector, let us call this as some C vectors. So, we have C transpose d lambda C, this is equal to Ci square lambda I. Now, I is going from k plus 1 to p now, and this obviously has to be less than equal to lambda k plus 1. Now, note that while we are writing this, we are considering the fact that for L, for every L orthogonal to E1 to Ek and as well as L transpose L is equal to 1. Okay. After considering these two set of criteria, we obtain this, and this gives us the maximum of variance of L prime x is maximum over L such that L is orthogonal to E1 to Ek and L prime L is equal to 1. This is nothing but lambda k plus 1, and lambda k plus 1 can again now shown to be equal to variance of Ek plus 1 prime x, giving us that Yk plus 1 is Ek plus 1 prime x is the k plus 1th principal component. We have talked about certain other properties of the principal components. If you recall, an important such property was that total variation of x is equal to total variation of y. So, we will begin our next session by proving that result.